this, can't solve it analytically. You should know this from some intro math classes. Well, the first thing we could do is, I mean, there's many ways to solve these things, but I'm just going to do an example for root finding. Okay, so let's move this to the other side. We can say x squared plus 3x minus e to the square root x equals 0. And what do? Well, we find the root. And there are a number of numerical methods to find roots. I'm not going to teach you all the theory behind root finding. I just want to show you how to use Python. Okay, so let's find the root of this equation where it equals 0. Instead of solving for where the two equations equal to each other, we'll solve for these cross. Okay, so so for this, let me turn on code here. Let's look at some code, how we would do this. So the functions, first we want to import our libraries. So we'll import, I'll zoom in here for you a little bit. NumPy is our classic. So import NumPy as NP. I'll show you some plots. So let's import matplotlib.py plot as PLT is kind of the common notation. And then to do root finding, the library you're going to want to use is SciPy. Okay, so from SciPy.optimize, this is the library which has the function we want. We want to import fsolve. And again, there's many different ways to do this in Python. I'm just showing you one of them that I've used a few times. Okay, so let's take this, arbitrary example. So first, let's define our function. So to define a function, we'll define, let's give it a name of the function. We'll say function1, and it's a function of x. So we want to say this is, will return, well, we say x squared plus 3 times x minus, this is the equation we just showed, np dot exp x to the 1/2. Okay, so this was the equation that equals 0. If you remember on the previous, I'm not going to, but the idea was this is the equation that we had, and let's plot this, okay, to see exactly what it looks like to get an idea. Okay, so to plot, we can do plot figure.
I'm curious
and,
also.
I like to number them so that we can add things to the plot. Number, I always put DPI equals 120 so I can use these figures for something, otherwise the resolution is really low. And then we'll say plot, and we need to give it a list of x values. Okay, so the x values, I know the intercept for this ahead of time, but you can check. It's going to be somewhere between 0 and 1. Okay, so let's make an x list that we can use.
Okay, the x here is your omega. X here is your omega.
This function linspace is going to make a linear list of values between 0 and 1. Then we can put a number. We'll say 1,000 points. So this would be a list between 0 and 1. Now let's plot this x list. And then this function evaluated at the x list. Okay, so now we've defined this function. So all we need to do is put in this argument. So this is going to be function1 and then evaluated at the points x list. So it'll give us a list evaluated at every point in this input that we put here. Okay, so this is going to be our plot, and I'm going to add a label. I'm going to say the label should be, this is our function1. Now I also want to plot the 0 so we can see where it crosses 0. So I'll plot the same x values. I'll plot 0. So I need an array of zeros. So I'll just take x list multiplied by 0, and this will just give us an array of zeros. That's the same length as the x value. This is our x values, these are y values. And I'll make this dashed. You can add a little dash in there like this to say, you can look up the matplotlib function, but I like to add a dash. And the label, I'll say this is, this would be like the y equals 0. And then to make these labels show, I'll say plot legend. Okay. So we can run this. This is in Spider. And if you go to the plots tab, it'll show up. And here we have it. Okay. So here's this equation we're trying to solve, which is blue is the function 1. and we see that between 0 and 1, there's going to be one root. Okay, so it crosses 0, which is the dashed line here, near 0.6, somewhere around there. Okay, so what we want to do is find a numerical method to solve for this root, or solve for x numerically, and this is going to be with fsolve. Okay, so how fsolve works is we've already imported it so that we can just directly call it. And we're going to say the root is equal to fsolve.
Okay, so the graph here is just to show you there's one root. There's one root of the function because he plot the line 0 and then he plot the x squared plus x plus exponent square root of x. Is the blue curve. So because it is equals to 0, so there is a cross at the 0 here, so there's one root here. And after this, then only the how to find the root.
And then look, it gives you all the information here. So you need to give it a function. You need to give it x naught, which is the initial guess, which is the method of using to find the roots, and then a bunch of other information. For this example, it's an easy one, so we just need to put the function 1. Now, you don't need to put an argument. You don't need to put the variable. So it's assuming that there is some variable. If there was a list of variables, it would just take the first one as the variable. So, you just put the name of the function and it knows it's a function of x or whatever the first variable you input in, okay? So this is function 1 would be all you write, and then you have to give it the initial guess, x naught. Now we know the root should be near 0.6. I'll say, it's maybe 0.5. Yeah. And that's it. We can evaluate this. And I'll go back to our variable explorer, and we can see root is equal to 0.603. Okay, and that's the root. Okay, so x equals 0.603. As easy as that. That's how you solve the equation numerically. Now, what I want to do is show you a more complex example. Okay, so let me get it up here.
You still have time,
Okay, so let's now take a more complicated example. This would be like a heat transfer example. I teach a heat transfer class. This would be what you see. Maybe you're in that class where you're looking at this. In this case, we have some sort of two-layer system. You've got one layer here, one layer here. The inside is at 35 degrees. The outside is at 10 degrees. And we want to know the temperature at this layer. Okay. So, the surface is cooling by radiation. It's cooling by convection. We know the area of the surface. Radiation happens via Stefan-Boltzmann constant. We know the heat transfer resistance through the material. We've calculated separately. And you can show with different math, not the subject of this particular equation. Okay. And what we want to solve for is what is the surface temperature. Okay, so you can see that this is in red. You see surface temperature here. You see surface temperature here. You see surface temperature here. So how do you solve for the surface temperature? We can't do this analytically like we do a lot of problems. So let's do it numerically. Now, one thing you need to do is take note that this is going to be in SI units. You notice Kelvin here and Kelvin here. Now, if you have a difference between two temperatures, you can do Celsius. But when you're adding them, especially squared, you need to put it in Kelvin. Okay. So to get the right units, 35 plus 273.15 equals 308.15 Kelvin, and 10 plus 273.15 equals 283.15. Okay, so let's use these, all this information we have here in this equation to solve for TS. And the reason I'm using this is because it's going to be a little more complex of function. Okay, so you can scroll back if you need to see this. Otherwise, I'm going to exit out of the function. Let's take a look in Spider. Okay, so now let's define another function. Okay, so this will be the heat transfer